Welcome to the Balance Fault video series. This is the first part of the video series where you will learn about various characteristics of balance fault, the modeling concept of fault, and in the second part of the video series, I will demonstrate how a balance fault analysis is performed on a simple 3-bus network, which we can extend to a larger network of buses. So let's begin. As an introduction, there are two types of fault that we should know. The first is the three-phase balance fault, which is discussed in this first part of the video. The second type of fault is the unbalanced fault, which is comprised of the line to ground, a line to line, and a double line to ground fault, and they are not discussed in this video series, but instead they are presented in the second video series. There are three important characteristics of balance fault that we should know. The first is that the balance fault is the simultaneous short circuit across all three phases. And due to this simultaneous occurrence on all three phases, we can sort of know that the probabilities of a balanced three-phase fault is normally quite low. And for this reason, we can say the balanced fault is infrequent compared to the unbalanced fault, but they are the most severe types of fault that we can encounter due to the happening of fault in all three phases. However, the silver lining behind the balanced fault is that they are balanced. And due to their balanced characteristics, the solutions of a balanced fault is the easiest among all types of fault. Because a circuit affected by the balanced three-phase fault can be broken down into their per-phase basis, and through which we can analyze using basic circuit theories. There are three important concepts of fault modeling that we need to know before going into the calculations details of balanced fault in the second part of the video. The first is that we model fault as a structural change on the networks. The reason is when fault occurs, the original power flows in the network will change, and in order for the change to take effect, the original elements of the network need to be updated as well before the original power flow can change to a new level to represent a particular fault that has taken place. So it is in this updating effect of the network elements that we say the network has undergone structural change. And then one of the basic or most important approaches in circuit analysis is that we normally use impedance to represent a particular effect on power flow. Therefore, going by the same logic, the structural change on networks that we mentioned earlier is also represented as an additional impedance at the place where the fault has taken place. And with the introductions of the impedance, we have managed to model the effect of fault in our circuit so that we may analyze them. And as you may have anticipated, the impedance values are updated based on the levels of the fault that we are seeing. And if the impedance is a variable and the remaining impedance of the circuit stays constant, then we can actually simplify our circuit further into a series system based on the Thevenin theorem. To illustrate the calculations of balance fault in the second part of the videos, we present this 3-bus network in this slide, and several parameters that we need to take note of. First of all these impedances are expressed in their imaginary values only, and therefore the resistance are neglected. The networks are in the no-load condition. That is to say that there will be no voltage drop across the line. and all generators are assumed to be operated in their rated value before the fault occurs. And one important thing that we need to take note is that the impedance of each generator, as given over here, they are in their transient values, which I will explain the concept of transient in the next slide. So this figure illustrates the life cycle of a typical fault, which is applicable to both balanced and unbalanced faults. As you can see, when faults propagate through their life cycle, they undergo three major phases, which are the subtransient, transient, and the steady-state periods. Subtransient periods is the first few moments immediately after the fault occurs, and it lasts only for a few milliseconds. And during this time, the fault current surges to a very high level and gradually reduces as it enters the transient period, which reduces further as the fault enters its steady-state period. The fault current in the steady-state period will remain there at a constant value until it is cleared by protection system devices. As mentioned in the previous slide, that we represent or we model fault as an impedance in our network. Similarly, the effect of fault, depending on which period we are looking at, can be represented by their corresponding impedance as well. So, depending on our analysis, if we want to analyze the effect of fault current during the subtransient period, we should use the impedance during the subtransient period in our network. Similarly, if we want to analyze the effect of the fault during the transient period, then we should use the impedance during the transient period in our network during our analysis. In the example shown over here, we are using the transient values. However, we can simply replace the transient values with subtransient or the steady-state values, and they will not affect our analysis method that we are going to see in the second part of this video series, because they will only affect the numerical values. With that, that is the end of this first part of the video, and I hope to see you in the second part of the video soon. Thank you for listening.